Imagine deploying a state-of-the-art AI detection model into your enterprise pipeline. You're trying to flag fraudulent insurance claims or maybe synthetic financial documents.
Right, something highly specific.
Exactly. So you set your decision boundaries, you validate the architecture, and you deploy. But instead of catching the fakes, you realize the algorithm is, well, it's mathematically hardwired to classify almost every real invoice as a fake.
And every generated fake as real.
Yeah.
It's wild.
I mean, that is literally the absolute worst-case scenario for binary classification. You haven't just lost statistical separation. Your model has actively inverted the ground truth.
Welcome to the deep dive. Today, we're opening up a stack of your sources, specifically looking at a really groundbreaking new paper that tackles this exact phenomenon.
Yeah, it's a fascinating read.
The paper is titled General and Domain-Specific Zero-Shot Detection of Generated Images via Conditional Likelihood. And the authors introduce a method they call CLID.
Which stands for Conditional Likelihood Generated Image Detector. Right. And for you, as a practitioner deep in the trenches of machine learning and data science, our mission today is really twofold.
First, we need to unpack exactly why the current state-of-the-art zero-shot detection methods fail so catastrophically on narrow domain-specific data.
Yeah, and second, we're going to explore the mechanics of how CLIE mathematically neutralizes that failure. Using conditional likelihood right within the latent space of foundation models.
It's an incredibly timely mission, honestly. Generative models, especially the advanced diffusion architectures we see today, they're just evolving at a pace that renders supervised detection datasets obsolete.
Almost the moment they're compiled, right?
Exactly. You simply cannot maintain an updated training set of synthetic images when novel generative techniques or, fine-tunes are emerging weekly.
Which is why zero-shot detection has become the required paradigm. The ability to distinguish real from generated images without ever training on the fakes is, well, it's the holy grail.
It is. Theoretically, if you understand the fundamental distribution of reality, any synthetic deviation should flag as an anomaly.
But let's look at the mechanics of the current zero-shot landscape to understand why that theory falls apart in practice.
Well, existing zero-shot strategies generally rely on analyzing an image's robustness to specific transformations. Instead of explicitly calculating the probability of an image, they use implicit probabilistic proxies.
Right, like Arrowblade. The paper discusses that one, which uses a pre-trained autoencoder and basically treats reconstruction error as the detection criterion.
Yeah, and then there's Rigid, which evaluates the similarity between an original image and a noise-perturbed counterpart.
We also have methods like ZED, estimating pixel-wise probability using lossless encoding, so essentially using file compression efficiency as a proxy for likelihood.
Right, and manifold bias, which looks at differential measures within a diffusion model's own probability space.
Now, if you're running these models on a massive, diverse data set of random internet images, they actually perform decently well.
They do, yeah.
But if you take those exact same algorithms and apply them to a highly constrained domain, like, say, only damaged cars or only scanned invoices, the math breaks.
It breaks severely. I mean, the paper provides the hard performance metrics. In narrow domains, the area under the curve, or AUC, for these prior methods routinely drops below 0.6.
Wow.
And in several critical instances, it drops below 0.5.
And just to underscore the severity of that, for anyone listening who builds these pipelines, an AUC of 0.5 is a random coin flip.
Exactly.
An AUC below 0.5 means your classifier is actively wrong. It means generated fakes are mathematically evaluating as more robust or more real than the actual real images.
That is the flipped classification the authors talk about.
Right. So to understand how this happens, we have to look closely at those implicit proxy functions.
Let's take Arrowblade's reconstruction error, for example. In a broad dataset, generated images often contain subtle, high-frequency artifacts that a standard autoencoder fails to reconstruct accurately,
Resulting in a high error rate for fakes.
Right. But what happens when you constrain the real domain to scanned invoices?
Well, a real scanned invoice is incredibly messy at the pixel level. I mean, it has scanner sensor noise, fold marks, inconsistent ink density, optical blur, all of that.
Exactly. Now compare that to a diffusion model prompted to generate an invoice. The diffusion model produces structurally perfect text, crisp lines, and zero genuine sensor noise.
Ah, I see. So to the autoencoder, that clean generated image is far easier to reconstruct mathematically than the messy real one.
Yes. The reconstruction error for the fake drops well below the error for the real image. The implicit proxy function fails because it fundamentally assumes that generative artifacts are always the primary source of reconstruction difficulty.
Which simply isn't true in narrow domains.
Not at all.
And I imagine the same logic applies to ZED and its lossless encoding proxy, right? Like a generated dent on a car might have smoother local pixel correlations because of how the diffusion process denoises the latent space.
Right, so it compresses beautifully.
Meanwhile, a real photo of a crumpled bumper is structural chaos, so it compresses poorly.
Yeah.
The proxy interprets the smooth compression of the fake as a higher likelihood.
That's exactly what's happened.
But I want to push back on this fundamental architecture for a second. If these zero-shot methods don't require any training on the fake images, why are they so hypersensitive to the boundaries of the real images?
That's a good point.
Shouldn't a real invoice always behave like a real invoice mathematically, regardless of what other data exists in the world?
That is a great question, and it highlights the flaw of manifold scale dependency. These proxy metrics are calibrated on the broad manifold of natural images.
Okay.
When you measure noise perturbation across everything from landscapes to portraits to macrophotography, you establish a baseline variance.
A global baseline.
Right, but when you constrain your input exclusively to invoices, that manifold collapses into a tiny hyperdense mathematical subspace. The implicit heuristics lose their global calibration.
It's like using a yardstick to measure cellular structures.
Yeah.
The instrument just isn't scaled to the local variance.
Exactly. So the solution requires abandoning these proxy heuristics entirely. And this brings us to the core premise of the CLID paper.
Right. The authors argue that we must move to an explicit probabilistic computation. We need to directly measure how probable a given image is under the true distribution of natural images.
And to do this, they shift their focus to foundation models, specifically CLIP contrastive language image pre-training.
The underlying theory here is solid. A foundation model trained on hundreds of millions of diverse real images inherently maps a highly complex, high-dimensional latent space.
Yeah, a space that captures the subtle attributes differentiating real physics from generated approximations. If we can access that mapping, we don't need proxies.
But utilizing that information is notoriously difficult, isn't it? Computer vision models, especially foundation models, are essentially black boxes when it comes to explicit density estimation.
Very much so. They primarily rely on likelihood gradients or score functions. Computing a direct, unconditional likelihood for a high-dimensional image in pixel space is computationally intractable.
However, prior research demonstrated that you can bypass pixel space by estimating image likelihood within the embedding space of CLIP.
Right. You map the input image to a high-dimensional vector in CLIP's latent space and analyze its position relative to the density of real images.
But here is where the authors of CLID hit a massive roadblock with unconditional likelihood. And it's something you really need to consider if you're fine-tuning foundation models in your own work.
Yes, the semantic bias problem.
The example they use to demonstrate this in the paper is absolutely fascinating. It involves a zebra and a plate of food.
It perfectly illustrates how CLIP's latent space prioritizes information. Because CLIP's architecture utilizes a contrastive loss function designed to align images with natural language descriptions, its embedding space is profoundly dominated by semantic meaning.
So it organizes data by what is in the image, rather than how the image was constructed.
Exactly, which means the mathematical topology of that latent space is extremely uneven. The density of semantic clusters varies wildly based on the pre-training data.
Okay, so how does that affect the zebra?
Well, the mathematical reality of CLIP's latent space is that the semantic cluster for animals, like a zebra, is significantly denser and more central than the semantic cluster for food.
Right.
Therefore, a picture of a zebra inherently has a higher baseline likelihood score than a picture of a plate of food, completely independent of whether either image is real or fake.
Oh, wow. So if we attempt to use raw, unconditional likelihood in the CLIP space to detect fakes, the model's semantic bias completely overrides its authenticity detection.
Precisely. If you evaluate a highly synthetic, blatantly AI-generated image of a zebra and a completely real, unedited photograph of a salad,
the generated zebra will likely yield a higher likelihood score, simply because it is a zebra. The model is evaluating the what and conflating it with the how.
that is the fatal flaw of unconditional likelihood in vision language models. The density of the semantic cluster masks the density of authenticity.
That's wild.
And this specific finding is the crucial justification for the authors moving to conditional likelihood.
Meaning you condition it on the domain.
Right. If you want to know if an invoice is real, you cannot compare its embedding against the entire universe of images. You must condition the likelihood estimations strictly on a reference set of real images from that exact target domain.
You have to lock the semantic vector in place, so the only remaining variance left to measure is the authenticity.
Exactly.
Okay, we've established the landscape, the failure of implicit proxies, and the necessity of neutralizing semantic bias. Now let's get into the mechanics of how Kielide actually achieves this.
The math.
Yeah.
Yeah.
How do we practically isolate the how from the what in a high-dimensional latent space?
Well, it begins by passing your input image through the CLIP image encoder to obtain a high-dimensional vector. We also maintain a reference matrix composed purely of real image embeddings from our target domain.
But, to your point earlier, we don't evaluate the input against the entire reference matrix. That would reintroduce broad semantic variance.
Correct. Because even within a domain like damaged cars, comparing a shattered windshield to a dented bumper creates unnecessary semantic distance. We need local density estimation.
So CLID employs a k-nearest neighbors approach.
Yes. We compute the cosine similarities between our input embedding and every embedding in the reference set, and we isolate only the top CAG most similar embeddings.
Restricting our mathematical focus to the immediate semantic vicinity of the input image.
Yeah.
We've effectively controlled for the what.
Exactly. So now we have an isolated neighborhood, but we still need to calculate the explicit likelihood of our input existing within this specific neighborhood.
This is where the core mathematical transformation occurs, right?
Yes. We compute the mean vector of this local neighborhood, and then we calculate its covariance matrix. From that covariance matrix, we extract the top m eigenvectors.
The dominant one.
Right. These dominant eigenvectors represent the principal dimensions where the actual authentic variance of this specific domain occurs. We use these to construct a conditional whitening matrix.
Let me stop you there and push back on this dimensionality reduction, because this is where a lot of practitioners might see a red flag.
Okay, sure.
By taking only the top m eigenvectors to build this whitening matrix, we're actively projecting the data into a lower dimensional subspace. We're assuming the remaining dimensions are just low variance noise and discarding them.
That's right.
Isn't it incredibly risky to assume that the artifacts of a generative model will conveniently manifest within those dominant dimensions? What if a diffusion model is mathematically sophisticated enough to hide its structural flaws in the null space we just ignored?
It's a highly sophisticated concern, and it strikes at the heart of why the manifold assumption works in this specific context. The reality of advanced generative models is that while they are excellent at replicating broad semantic features, they actually struggle profoundly to perfectly match the highly specific correlated variance along the principal components of a narrow real-world manifold. Generative artifacts don't just hide quietly in the null space, they actively disrupt the dominant covariant structure of the real data.
So they can't help but leave footprints in the main subspace.
Precisely. And the conditional whitening matrix is designed specifically to expose those footprints. It doesn't just project the data, it scales those dominant dimensions by the inverse square root of their eigenvalues.
So if you visualize the local neighborhood of real images as like an elongated asymmetrical cloud in the latent space, the whitening matrix morphs that cloud into a perfect isotropic Gaussian sphere.
Yes, it normalizes the variance across all principal directions.
Which makes the final calculation incredibly elegant.
Yeah.
Once we've forced the real reference data into an isotropic Gaussian distribution, computing the conditional log likelihood becomes straightforward.
We apply that same whitening matrix to our input vector.
Right, and the math in the paper shows that computing the squared Mahalanobis distance in the original latent space simplifies perfectly.
To computing the squared Euclidean distance in this new whitened subspace,
Yeah.
for those tuning into the mathematical architecture, that is the brilliant simplification. Because we established that the real images follow a normalized Gaussian distribution in this subspace, any generated image that lacks those exact, highly correlated authenticity vectors will be projected far away from the origin.
Its squared L2 norm in the whitened space will be massive.
Exactly. Which mathematically translates into a heavily penalized, exceedingly low log likelihood score.
You simply compare that score to a dynamic threshold derived from your real reference set, and if it falls outside the Gaussian sphere, you label it generated.
It completely bypasses the need for arbitrary compression proxies or noise perturbations. We are explicitly measuring statistical belonging.
But of course, assuming a local neighborhood perfectly conforms to a Gaussian distribution is a massive theoretical leap. Does this assumption actually hold up when the algorithm encounters messy, overlapping domains?
The authors knew they had to validate this rigorously. They designed an experiment using ImageNet-R, focusing on two domains that share massive semantic overlap but differ entirely in execution sketches and paintings.
Because if semantic bias was still dominating the calculation, the embedding of a sketched bird and a painted bird would occupy the exact same density space.
Right. But the results detailed in the paper proved the conditional whitening completely separates them. They computed the whitening matrix using the local neighborhood of the sketch domain and then applied it to the painting images, and vice versa. The statistical normality test confirmed that within the chosen dominant dimensions, the whitened coordinates are indeed approximately Gaussian. More importantly, the 2D scatter plots and 1D histograms demonstrated massive, unambiguous cross-domain separation. When you evaluate the likelihood of a painting under the conditional whitening matrix calibrated for sketches, the likelihood score absolutely plummets.
Which definitively proves that conditioning the likelihood on the local neighborhood successfully isolates the phenomenological attributes, the physical how it was made, from the semantic what it is attributes. A painting doesn't share the same covariance structure as a sketch, even if they both depict a bird.
Exactly. With the underlying math empirically validated, the authors then deployed CLA against the domain-specific failure modes that crippled the baseline models.
And to ensure the test was representative of real enterprise challenges, they built entirely new synthetic datasets.
Yeah, they didn't just use standard benchmarking datasets. They generated 6,000 images of damaged cars across 5 different generative architectures, alongside 3,000 highly realistic synthetic invoice images.
If you're an engineer tasked with securing financial compliance systems or building automated claims processing, this is exactly the data distribution that keeps you up at night. How did CLA perform against the models that suffered flipped classification?
The contrast is stark. In a general setting classifying broad, diverse sets of images, Clyde outperformed Aeroblade, Rigid, ZEd, and Manifold bias.
Okay, but what about the narrow domains?
In the domain-specific tasks, Clyde effectively solved the mathematical collapse. On the damaged cars, the artistic distributions, and the synthetic invoices, CLIA-D consistently sustained a high AUC, remaining well above 0.9 across the board.
While the implicit proxy methods absolutely crumbled, they maintained that 0.5 AUC, confidently classifying the perceived fake invoices as mathematically more authentic than the newsy real ones.
Yeah. But there is a crucial implementation detail for practitioners here, specifically regarding the composition of the reference matrix. The math only works if your reference set accurately represents the local manifold.
Right, that's detailed thoroughly in Table 4 of the paper. The conditional likelihood calculation is highly sensitive to the relevance of the reference set.
The authors demonstrated that if you attempt to evaluate a domain-specific image, like a scanned invoice, using a reference matrix composed entirely of general, random internet images, CLID's performance drops precipitously,
yielding an AUC of around 0.34.
Because the k-nearest neighbors search fails, there are no local neighbors in a general data set that accurately map to the highly specific, correlated variance of an invoice subspace.
You end up calculating a covariance matrix on semantic noise.
Exactly. However, the operational fix is surprisingly lightweight. The authors found that by injecting just 1,000 domain-specific real invoice samples into the reference set, the AUC rockets from 0.34 up to 0.91.
Oh, wow. So you don't need a massive, exhaustive data set.
No, just 1,000 authentic images provide enough density for the algorithm to accurately define the local manifold and restore the statistical separation.
And they took it a step further to prove operational robustness. If you build a combined multi-domain reference set, mixing general images, the damaged cars, the art, and the invoices all together, CLAT still maintains an AUC greater than 0.9 across every single domain simultaneously.
It proves that the initial KNN search isolates the correct semantic neighborhood reliably, even when the broader reference matrix is highly heterogeneous. As long as there is a minimal critical mass of domain-relevant samples available to anchor the covariance calculation, the conditional whitening matrix will successfully isolate the authenticity vectors.
So let's synthesize the primary technical takeaway from this deep dive. The fundamental contribution of the CLID paper is demonstrating the danger of relying on implicit proxies for zero-shot detection.
Measuring how an image reacts to noise or compression assumes a global calibration that simply does not exist in narrow enterprise datasets. Generative models will exploit those proxies, resulting in catastrophic flipped classifications.
The required standard for robust detection is now explicit probabilistic computation. By estimating the conditional likelihood of real images within a highly specific whitened embedding subspace, CLID successfully neutralizes the semantic bias inherent in foundation models like CLIP.
It forces the evaluation metric back to the structural authenticity of the data manifold.
Domain adaptive representation learning is no longer an optional optimization. If you're deploying these systems, it is a mathematical requirement.
Right.
You have to anchor your detection in the statistical reality of your specific domain.
Absolutely.
But as we wrap up, this elegant mathematical solution brings up a rather unsettling theoretical scenario that I want to leave you with.
Oh.
We just spent this entire discussion establishing how CLI Guide so precisely maps the local Gaussian distribution of real images in a narrow domain using a deterministic conditional whitening matrix. The boundary of reality is now explicit and mathematically knowable.
Yes.
So if that's true, could an adversarial generative model compute that exact same whitening matrix? And if it can compute it, could the developers inject that matrix directly into the model's loss function during training?
That's wow.
Could they explicitly force the diffusion process to optimize its outputs entirely within that safe whitened isotropic subspace?
Yes.
If they do, they would theoretically render the synthetic artifacts completely mathematically indistinguishable from reality, at least according to this paradigm.
It is a profound vulnerability. When the defense relies on a knowable geometric transformation, you provide the adversary with the exact coordinates of the blind spot. That is undoubtedly the frontier the next generation of adversarial networks will attempt to exploit.
A sobering thought for the next time you're defining a loss function or updating your detection pipeline. That's all for this deep dive.